Good evening, everybody. And once again, I would like to welcome you to another online review session. For today's session, we shall focus on the chemistry of carboxylic acid and derivatives. This will be taken from our end of chapter problem, which is chapter 21. So, okay, let us get the session going. I did notice here a lot of people have since joined us. Let us see here before we get started. Okay, I see Fola is joined us, Courtney has joined us, Shilanda, Lauren Prince, Stephanie. Okay, you are all welcome. Okay. To get the session rolling, let us start with this question here. So I'm going to call on Stephanie. Can you go ahead and read this question for us? If your mic is working.
Name the following compounds.
Okay, very good. So what they want us to do now is to name the following two compounds. This one here. I also notice Robert is joining us, and also to name this compound here. Okay, to start with, looking at this compound here, the blue color here is nitrogen. Of course, you have your carbon-oxygen double bond. Does anybody know what class of compound this is? Can you give us an idea what class of compound this is? Nitrogen bonded to, okay, excellent, excellent. You guys say it's an amide. Yes, it is an amide. Anytime you have the nitrogen bonded to carbon-oxygen double bond, and of course the carbon-oxygen double bond is bonded to a carbon atom, then you have an amide. Very good. Of course, we also notice here we have a phenyl group. To look at this here. We have the phenyl group, which is essentially a flat molecule, part of the molecule right here. Okay, so about this molecule here, the green here is chlorine. Here we have oxygen, which is red, and then we have the carbon-oxygen double bond. Does anybody know what class of compound this is? Does anybody know what kind of compound this is? An ester. Excellent. Okay, this is an ester. Of course, you know that an ester is when you have the carbon-oxygen double bond bonded to oxygen, and that oxygen is bonded to another carbon, and also the carbon-oxygen double bond is bonded to a carbon atom. Okay, so to solve both of these problems, since what they want us to do is to give the names of this molecule, let us go to my notebook so we can do these problems together. Okay, so this is the problem right here. The first thing I'm going to do, I'm going to write the two-dimensional structure here. Okay, starting with the benzene. And that is this benzene right here. And that is, of course, joined to a CH2, which is a methylene group. And that methylene group is joined to another CH2, and that is in turn joined to the carbonyl, and then the carbonyl is joined to the nitrogen. The nitrogen is joined to hydrogen here, and of course the nitrogen is also joined to a methyl group. Okay, now you guys already told us that this is an amide, which is correct. Okay, now what kind of amide is this? Is this a primary amide, secondary amide, or tertiary amide? Anybody has an idea? What kind of amide is this? Primary, tertiary, or secondary? Taking a look at this nitrogen here. Okay, secondary, very good. Okay, secondary amide, because this nitrogen here is bonded to two other carbon atoms, this carbon and this carbon. So therefore, this is a secondary amide, which is this one here. Okay, now let us name this molecule. By the way, this is this molecule here that we've just drawn. This one here. Okay. Now, to name this molecule, you have to name this based on the longest carbon chain that contains the corresponding carboxyl group. Or somebody will ask a question to ask me. Okay. Oh, Stephanie, turn your mic off. Unless, okay. Okay. So now we have this amide here. So to name this, we look for the longest carbon chain that contains the carbonyl group, which is this here, because we are going to name this based on the corresponding carboxylic acid. Okay, so the corresponding carboxylic acid will have this chain. This will be carbon 1. Oh, let me change my pen. Carbon 1, 2, and 3, which means that we have the phenyl group. This group here, that is the phenyl group, will be a branch or a substituent, and that substituent is in the 3 position. And so to name this, what we need to do, we also take a look at the nitrogen atom. Now, if this was, for example, if we have this, let me just give you this, a little bit of a background. Supposing we have this. If we have this molecule here, now this is an amide. Now, what kind of amide is this? This one I've drawn here. Primary, secondary, or tertiary? Primary. Okay, very good. Now, if we want to name this, of course, we want to name this based on the corresponding carboxylic acid. So the corresponding carboxylic acid name is propanoic acid. Okay, propanoic acid. And to name it as an amide, what do? We remove the word acid. Then we also remove the OIC, the suffix OIC, the last 3 letters of the corresponding carboxylic acid name, OIC. We remove that, and then we replace with the word amide. Now this becomes amide. One word. So this particular molecule becomes propane amide. Now, supposing now I have this. Now, if you follow this, give me a happy face. Okay, this is propane amide. If you follow that, give me a happy face. Okay, very good. Now, supposing now I take off this hydrogen from here, and now I have a methyl group to replace the hydrogen. So now I have a secondary amide. So once I have a secondary amide, if I have to name this now, if I have to name this molecule, this is what I would do. Keep in mind that the parent amide name is propane amide. So if I need to name this, what I would do is to give the name of the alkyl group that is attached to nitrogen. I say N-methyl In other words, a methyl group is attached to nitrogen. Then I give the parent name of the amide, because propane amide. Okay, if you follow that, give me a happy face. In other words, we give the name of the alkyl group attached to nitrogen, say N-methyl. Notice here, this is one word. Now, supposing I remove another hydrogen. Supposing I remove another hydrogen and I place this here, and supposing I have an ethyl group here. Now, what type of amide do I have now? This is still an amide. What type of amide do I have now? Primary, secondary, or tertiary? Primary, okay, tertiary. Because now this nitrogen is attached to 3 carbon atoms. So this is a tertiary amide. Okay. So now for me to name this, this will now becomes, we have an ethyl group attached to nitrogen, another methyl group attached to nitrogen. So how do I name this? I will do this. Let me take this out. I will say, keep in mind we have to follow alphabetical order. N, ethyl. In other words, ethyl group is attached to nitrogen. N-ethyl, N-methyl, okay? Then we give the name of the parent amide, which is this here, propane amide. Okay, all one word, N-ethyl, N-methyl, propane amide. Okay, all one word. Okay, so now that I've given you that background, let us come back to this molecule here. Yeah, go ahead. Somebody asked a question. Go ahead.
Do we put a dash between the ethyl and the other N, or is it just a space?
Yeah, I'm sorry, say dash in there. Thank you. Okay, N-ethyl, N-methyl, propane amide.
I'm really bad.
Very good. Now, okay, now let us now come back to this molecule here that we need to name this molecule. Let me make some space here. Okay, I'm going to remove this. I am taking some time to go through this because we did not do this in class. Okay, this is the amide right here. Okay, so now the parent amide, if we look at keep in mind you have to start, the parent amide will be the primary amide. Okay, if it was the primary amide, there will be 2 hydrogens here. So the parent amide will be this carbon number 1, 2, 3, that's propane amide. We have a phenyl group attached to the 3 position. So we say 3-phenyl, propane amide. That will be the base name. And then we now indicate the position of this methyl attached to the nitrogen. So now we say N-methyl 3-phenyl propane amide. Now, do you follow that? That would be the name of this compound now. Now becomes N-methyl, that is a methyl group is attached to the nitrogen, then you give the name of the base for the base amide, which will be your primary amide. If you follow that, give me a happy face. Okay. Okay, very good. Okay, I see a lot of people have since joined us. Let us acknowledge these folks. I see, okay, of course, Emma is here, Fola Deoshin is here, Courtney, Jasmine has joined us also. Let's see here, Julian is here, Julius Evans is here, Lauren Prince, very good. A lot of people here today. Melat joined us, Robert is here, Shilanda, okay, Shine, okay, Simon Cohen, okay, Stephanie Miller, very, very good. Okay, I see Lauren Baldwin is also joining us. Okay, so now we have named this molecule here. Now let us name this. Okay, I'm going to rely on you guys to help me with this one here. Okay, so let me erase this from here. Take this out of here. Okay, you guys already told us that this is an ester. This is an ester. This is the class of compound here. This is an ester. Okay. Now, if that is the case, what will be the name? Before we do that, let me write the three-dimensional and the two-dimensional structure right here. Okay, starting with this part, methyl. Attached to carbonyl. Attached to oxygen. Then that oxygen is attached to the benzene ring. Okay, and the chlorine atom is in the fourth position relative to the oxygen here. So that is chlorine. Okay, does anybody have an idea how to name this molecule? I will give you a hint. The first thing you do is to give the name of the branch that is attached to oxygen, which is this here. Okay, and then you also need to recognize the name of the corresponding carboxylic acid, which will be this part here. Okay, maybe I should ask you this here. What will be the name of the corresponding carboxylic acid? What will be the name of the corresponding carboxylic acid right here? Okay, how many carbon does it have? 1 and 2. Any idea? Okay, acetic acid. Excellent. Okay, this is acetic acid. In other words, this molecule here is an ester of acetic acid. Okay, very good. That's Lorraine. Okay, so the name of the corresponding acid is acidic. Acidic acid. Now, since we all agree that this is an ester, you know that to name an ester from the corresponding carboxylic acid, what you do, you remove the word acid, and you remove the IC, the suffix here, and then you replace with ATE. So anytime you see ATE at the end of a name, you know you have an ester. So this becomes acetate. Okay, so this part of the molecule is the acetate. Now we need to name this part of the molecule. How will you name this part of the molecule? If the chlorine was in there, we will call it phenyl. Right? Now that we have the chlorine there, what are we going to do? How will you name it? and the chlorine is in the 4th position. Okay. Okay, so we have 4 chlorophenyl. Okay, that is the name of the group that is attached to this oxygen here, and that is what this is. And that name will be separate from the base name, which is acetate. So this becomes 4-chlorophenyl acetate. Okay? Supposing I have this molecule. Supposing I have this molecule. How will you call this? Okay, what would be the name of this molecule here? That is an ester. What would be the name of that molecule? Could you also name it? Yes. Somebody is asking, Lorraine said, can I also call it p-chlorophenyl? Yes, you could do that. That is also correct. You could call it p-chlorophenyl. That is correct. Yes, I think Emma giving us this name here. It says ethyl butanoate. Excellent. Because this is derived from butanoic acid. So that becomes ethyl. Okay, which is this part of the molecule here, the alkyl group that is attached to the oxygen. And then we say butanoate. Okay, notice these are separate words. Okay, you separate the alkyl, the name of the alkyl group from the base name. Okay? Is there any question on this? Okay, so we can move on. Okay, let us do a series of nomenclature problems before we get to reactions. Okay, let us go do this. Okay, Emma, go ahead and read this question for us. Okay, Emma is not ready. But Julianne, go ahead and read this question for us.
Give IUPAC names for the following compounds.
Okay, very good. Give IUPAC name for the following compound. Okay, so the first question I want to ask you is this. What class of compound is this? What class of compound is this? Ester. Excellent. Ester. Okay. What is the name of the alkyl group? Oh, okay. Emma, I see that. What is the name of the alkyl group that is attached to the oxygen? What is the name of the alkyl group that is at? Okay, very good. So we have methyl. Okay. So we say methyl. Okay. Now, the corresponding carboxylic acid, keep in mind this name will be derived from the name of the corresponding carboxylic acid. The corresponding carboxylic acid will come from here. Does anybody have an idea what that name will be? I will give you a little hint here. Anytime you have a ring system attached to carboxyl group, this is a carboxylic acid, what you do, you give the complete name of the ring system. What would be the name of this ring system here? What would be the name of this ring system here? Cyclopentane. Excellent. Cyclopentane. Cyclopentane. That's Jasmine says cyclopentane. That is correct. Now, once you now give the complete name of the ring system, now you now add the word carboxylic acid. You now add the word carboxylic. Carboxylic acid. Okay. Now, if you now have to name this as an ester, say I have this. Let us say now I take this out. I have a metal here. Now you're now going to have to name this. Of course, you give the name of the alkyl group, which is methyl. Keep in mind that would be a separate word from this. Then you give the name of the corresponding carboxylic acid. This now is cyclopentane carboxylic acid. Now to show that this is an ester, just as we did before, you remove the word acid, take this out, and then you have ACE. So that becomes methyl cyclopentane carboxylate. Methyl cyclopentane carboxylate. Okay, now, having given you that information, what would be the name of this molecule here? What would be the name of this molecule here? Any idea? Okay, we have a methyl here. We have the methyl here, and then the corresponding carboxylic acid name will be methyl cyclopentane carboxylate. Almost there, almost there. You are almost there. The only thing that you need to do now is to indicate the position of the double bond. Okay? You now need to indicate the position of the double, exactly. Methyl 1-cyclopentane carboxylate. Because this is position 1, position 2, position 3, position 4, position 5. Okay? So now that becomes methyl, separate word, 1-cyclopentane carboxylate. Okay, the carboxylate showing that it is an ester, the ATE, the one showing that the double bond is in the one position. Okay, so that is fine, very good. Now let us name, if that is clear to all of you, give me a happy face. Okay, if there's a question, give me a red X. Okay, no, okay, very good, very good. Now let me take this off. We go to the net. We go to this one here. Okay, this out. Okay. So let us name this here. Now, keep in mind to name this. Look at this here. How many carbon atoms do we have here? Of course, this is what we call a diester. This is an ester functionality right here. Another ester functionality here. So this is a diester. In other words, you have two ester functions within the same molecule. Okay? So now what do? We are going to name this based on the corresponding carboxylic acid, and the corresponding carboxylic acid will be this here. Will be this, and this here. Okay. Now, supposing I ask you to name this carboxylic acid, what would be the name of this carboxylic acid? I'll give you a hint. You look for the longest carbon chain that contains both of the carboxyl group. Okay, so what is the longest carbon chain that contains both of these carboxyl groups? How many carbons do we have here? How many carbons do we have here? 4. We have 4 carbons. Very good. If we have 4 carbons, right, we have 4 carbons. Okay, this is carbon number 1, 2, 3, and 4. Okay, now, how will you name this? Supposing this was an alkane with 4 carbons, what would be the name of that alkane? Butane. Okay, so now what do? We say butane, since that would be the name of an alkane. Okay, now we have 2 carboxyl groups at the end of the butane. Now we say dioic acid. Butane dioic acid. In this case, whenever you have 2 carboxyl groups within a molecule, you look for the longest carbon chain that contains both of those carboxyl groups, and then you simply start off by giving the name of the corresponding alkane, and then you add the word di to show that you have 2 carboxyl groups, oic acid. Okay, having given you that information, what are you going to call this molecule? Given the fact that the name would derive from this here, butane dioic acid. Okay, so what are you going to call this? What are you going to call this? Dimethyl butane di. Okay. Keep in mind, what do we say you should do? You remove the dioid. Is that okay? I see that. Okay. Okay, I see dimethyl, because you have 2 methyl here. Dimethyl. Okay, separate word butane. Dioid. Dioid. Okay. I see you are close. Okay, butanoid. Okay. Okay. Okay, so this becomes dimethyl butane dioid. Okay. Because all you're doing here, remove this IC, remove this one here, and then you replace with ATE. Okay, that's what we've done here. Okay, now we've done enough of our nomenclature. Let us begin to see if we can go to some reactions here. C11. Okay. Is there anybody whose mic is working that I have not called yet? Go ahead and read this question for us. I see Karen is joining us.
From the list
Anybody
of available
whose mic is working?
Select the ones you would use in a preparation of acetophenone, phenol methyl ketone from bromobenzene.
Very good. That's Melat. Okay, very good. Okay, so now what we have here, they have given us a list of reagents, and now what they want us to do is to start with in the preparation of acetophenone. They want us to prepare acetophenone. Of course, I will expect you to know the structure of acetophenone, which is this here: benzene, attached to carbonyl, attached to methyl. That is acetophenol. Phenol, or sometimes we could call this phenyl methyl ketone, which is what they have here. Now they want us to make this molecule form. Let us take this off. We don't want to see this. Don't look at this here. They want us to make this molecule from bromo benzene. So they want us to give a synthetic scheme going from bromobenzene to this molecule here. So anybody has an idea, what do we do first? Let us start from here. Starting with bromobenzene. Now, keep in mind, nobody is asking you to draw the reaction mechanism. All you are being asked to do, yes, is to draw the scheme. Grignard, excellent. So the first thing you want to do is make a Grignard, okay? Okay, that is good. So we'll make a Grignard reagent. Okay, now that we made a Grignard reagent, what do you do now? What is the next thing we do? Keep in mind, this is where we want to come, right here. Now that we've done that, what do we want to do now? Grignard, okay. Keep in mind, this is where we want to come. Let me ask you a question. If I ask you to make this compound, right here, a ketone, with just starting with only one step, give me one step that will allow you to go to make this molecule here. One step. You have one starting material here, one reagent. Okay. Okay, Friedel-Crafts. Okay, you want to use a Friedel-Crafts reaction. Okay. So if you use a Friedel, okay, let me see if I could go along with that. That is not saying that you are correct. Let us say if you do that. Because whether you are correct or not, that will still be a good a learning experience anyway, so we get a chance to review our reaction. So, if you want to do Friedel-Crafts, fine. That is fine. That is an excellent choice, but that doesn't mean that that is what we want to do right here. Okay. Okay, so Friedel-Crafts will go from here to here. We get that. But keep in mind what they've told us to do. They want us to start from here. Okay, so at this point we cannot use Friedel-Crafts here because we have to start from here. And keep in mind that you've already started with a Grignard, which I believe is possible for you to do that. Okay, shouldn't we add ethanol to the Grignard? Okay. If you add ethanol to the Grignard, ethanol. Okay, that is correct. That ethanol, in other words, you want to add an aldehyde. Good. Change my pen. That is correct. Now you want to use an aldehyde because what you need here, you need 2 carbons. And ethanol contains only 2 carbons. Okay, so we have ethanol, which is an aldehyde, step 1, and then step 2, you add hydronium ion to finish up the reaction. Okay, and what would that give you? What would this give you? What would this give you? An alcohol. What kind of alcohol? Primary, secondary, or tertiary? I'm going to take this off. When you react a Grignard with an aldehyde, what kind of alcohol do you obtain? Secondary alcohol. Very good. You get a secondary alcohol. So, we are going to obtain this molecule here. We have the benzene. Okay, now we're going to let me change the color of my pen. We now have, this is coming from the aldehyde. Okay, that is correct, that is good. So now you get a secondary alcohol. Keep in mind, this is where we want to go. Okay, what step do we need to now take to go from here to here? How many steps do you need, or what kind of reagent do you need? Going from a secondary alcohol to this ketone. Okay, anybody has an idea? Chromic anhydride. Very good. Chromic anhydride. So now you use chromic anhydride. Or chromium trioxide in some kind of acid. Okay. What other reagent could you use? Is there any other reagent you could use? That is correct, by the way. That is correct. That's Brea. That is correct. But what other reagent can you use? PCC or PCC. Okay. What other reagent can you also use? Since this is a review, we are doing some revision here. Or what other reagent can you use? Do not look here. Des Martin. Very good. Des Martin. Okay. Des. Okay, so these are the three different reagents you could use to go from a secondary alcohol to a ketone. Okay, so far, now what have we done now? For our synthetic scheme, we go from the bromobenzene, react with magnesium, we form phenyl magnesium bromide, which is our Grignard reagent. Then we react the Grignard reagent with an aldehyde, followed by hydrolysis with water to get our secondary alcohol, and then we oxidize the secondary alcohol to get the ketone. Okay, that is very good. Let us see, do we have everything we need here? Let us see, do we have everything that we need? Let's see here. Okay, so we start with this one here. Grignard, do we have the, yes. That is G. Okay, then after that we then have the ethanol or acetaldehyde. This is also called acetaldehyde. Okay, do we have acetaldehyde here? Very good, we have that. Okay, of course they did not give us the hydronium ion. They are assuming here that you simply just work up the reaction with hydronium ion. Okay, so we have that D. And then at this point we say we want to oxidize the secondary alcohol to a ketone. What do we need here? We have this, we have this Martin, yes. So folks, I do hope this has helped you to review some of your reactions. Keep in mind you need to keep those reagents very, very handy. Okay, keep in mind every time you come to me for any kind of assistance, the first question I ask you is, where is your table of reagents? Because once you have your table of reagents, the rest of it is very, very easy, particularly when it comes to designing synthetic schemes. You find them very easy to do. Okay. If this is clear to you, give me a happy face. Okay, very good. Now let us go to... Okay, I want to go to here. This is a spectroscopic question, NMR question. Now let us see, who can I call? Kia, is your mic working? If it is working, can you read this for us? Okay, apparently not. Okay. Jasmine, is your mic working? If it is, read this for us.
A compound C11H12O2 has an IR spectrum showing a peak at 1710 centimeters. Its NMR spectrum has peaks at delta 1.3, 3 hydrogen triplet, 4.3, 2 hydrogen portlet, 6.5, 1 hydrogen doublet, 7.4 to 7.6, 5 hydrogen multiplet, and 7.7, 1 hydrogen 1 hydrogen doublet. Storage structure.
Excellent. Very good. Very good. Okay. Now, this problem here, let us start with this formula. They have given us the spectroscopic data, they have given us the IR data and the NMR data. This is the formula. The first thing we need to determine here is what is the index of hydrogen deficiency. IHD, which I give the formula as C for the number of carbon atoms. Okay, great, 6. Excellent. Okay, for the benefit of those of you who might have forgotten this formula, let me just finish this. H, number of hydrogen divided by 2, number of halogen divided by 2, plus number of nitrogen divided by 2, plus 1. In this case, I know Emma has given us the answer, but let us see here. In this case, the number of carbon is 11. It is minus number of hydrogen divided by 2, that is 12 divided by 2, that is 6. There is no halogen, so we don't need to worry about this. There is no nitrogen, so we don't need to worry about this. So we just add plus 1. So therefore, 11 minus 6 plus 1, if you do that calculus or do that computation, you will end up with 6, which is what Emma has given us. Very good. So this means that we have a bunch of double bonds or unsaturation in this molecule. It could be 6 double bonds. It could be a triple bond and double bond, rings, and all kind of stuff. Okay, so now let's just look at the NMR data. What I'm going to do now, I'm going to write the NMR data in a tabular form, 1.3. Triplet, 3 hydrogen. So once we do it this way, it will be much easier for us to see. Then here, 4.3. Quartet. Two hydrogen. Okay, so we're taking care of that. Then we have 6.5. Doublet. Say that is 1 hydrogen. Okay, then we have 7.4 to 7.6. Let's just call that 7.5. Let's just make it 7.5. Okay, 7.5. You say multiplet. Five hydrogen. Then this is 7.17. Doublet. 1 hydrogen. Okay, of course they also give us the IR data here. So what does this IR data tell us? Can anybody give me any kind of suggestion as to what this 1710 wave number, what does it mean? What does it give us? What does it tell us about the molecule? What does it tell us? Carbonyl, exactly. So we have a carbonyl. So that much we know about that much. Now, what is the next most obvious information? Take a look at the NMR data. Take a look at the proton NMR data. What is the most obvious information you see here? In the NMR data. Okay, what is the most obvious? 7.5. Very good. But what does that tell us? What does 7.5 tell us? What does it tell us? It is very, very important. That is a good one. What does it tell us? Okay, arene. Okay, that means you have benzene, right? Very good. Okay, but then what does it tell you about the benzene? It says it has 5 hydrogen. So what does it tell you about the benzene if it has 5 hydrogen? Okay, it says it has 5 hydrogen. It's substituted. Very good. We are getting close. We are getting close. How many substitutions do you have on the benzene? 1. Exactly. Very good. So that means whatever happens, we only have 1 substituent on the benzene, because all of this other hydrogen here is what we see here as 5 hydrogen. So far, so good. We know we have carbonyl, right? So keep in mind we said we have the index of hydrogen deficiency of 6. Okay, let us see. Are we taking care of those? We have the benzene ring, that is 1. Then you have these 3 double bonds, that is 4. Then we say we have a carbonyl, that is 5. So what does that leave us? We have 1 index of hydrogen deficiency left. So what does that leave us? A double bond. See, we solved this problem. That means we have a carbon-carbon double bond. So all we need to do now, put all of the pieces together. We have the benzene, we have the carbon-carbon double bond, we have the carbonyl. So this problem should be solved. Now, having said that, let us now take a further look at this molecule. What are the other obvious information that we see here? What are the other obvious information that we see here? We have 3 hydrogen, triplet. 2 hydrogen, quartet. What does that tell you? What does that tell you? Quartet, a triplet. That is that excellent. So you guys have given us all the fragments. That means we have, for us to have 3 hydrogen here, so you have a CH3, which is a triplet. That is, it is attached to a CH2. Okay. So this is the triplet, and this is the quartet. So what this is telling us is that on this side of this molecule, this here, there is no hydrogen. This carbon here is not attached to an hydrogen and a carbon that contains hydrogen. So now most of our problem is solved. Let's put all the pieces together. Okay, let me make some room. I want to figure out just about all of our pieces. We have just about all of the pieces. Keep in mind, this molecule also has 2 oxygen. Okay, so far we have accounted for only 1 oxygen. Okay, so now, how do we do? Let us see. We'll start with this, benzene. We say it is attached to. Okay, we have a few choices here. I could say a carbon-carbon double bond, right? That is so far so good. Then I say I have a carbonyl. I say I have a carbonyl. Keep in mind, this 4.3, 2 hydrogen, that is telling me that these 2 hydrogen here must be close to oxygen to be 4.3. So therefore I have this here. Sorry about that. Okay. So I must have a carbonyl here, and then this oxygen here. Keep in mind, I must have this, right? So if I must have this, that CH2 must be attached to oxygen, and then this here. So what have I done? I've taken care of the methyl, which is this here. I've taken care of the ethyl, which is this here. I've taken care of the 5 hydrogen on the benzene, which is this here. What I'm missing? What I'm missing? 2 hydrogens, doublet. 1 hydrogen here 6.5, 1 hydrogen here 7.7. If you look at this molecule, the only places those 2 hydrogens could be here, because this carbon doesn't have all of its valence yet, and here. Okay? That is the only place where the hydrogen could be. So if you look at this, we have now accounted for everything, because this hydrogen here is a doublet because it is only seeing 1 hydrogen. Keep in mind the M+1 rule. Okay? And this hydrogen here is also a doublet because it is only seeing this hydrogen. So at this point, I could begin to now make my assignment. Okay, that this 7.7, at this point, if you say any one of these will be fine with me, if you say this is the hydrogen at 7.7, and this one at 6.5, okay, any one of, if you say this is 7.7 or 6.5, I will give you your full credit at this point. Okay, now of course this is your 4.3, and this is your 1.3, and these hydrogens here are your 7.5, and so we've accounted for everything. What would the multiplet indicate? Okay, very good. What the multiplet indicates is that all of this hydrogen here, the question that Priska is asking, we have multiplet. Keep in mind we have all of this hydrogen here. Okay? What it's simply saying is, they are, see, this here will see this will see this, and therefore their signals are overlapping each other. That's essentially what that means. Sometimes they might refer to it as complex. It simply means that you have overlapping signals. But because this hydrogen will see this hydrogen will see this, okay, this will see this will see this. So you have a very complex spectrum in that region. Okay, and that is what they mean by multiplet. Okay. Okay, is this clear to all of you? If it is clear to you, give me a happy face. Okay, very good, very good. Now you see what we did methodically. I went by solving this problem to one step at a time. Look at the most obvious information. Then you go from the most obvious information. You begin to put all of the pieces together. Okay. Let's see here. Let's do. Oh, that was 15. About 17. Oh, this time goes so fast. Okay, let us do this here, 17. Okay, let me see. Mellard has talked already. Karen, is your mic working? If your mic is working, can you read this question for us? Okay, I don't think that is working. Okay. Lauren Bolden, can you read this for us if your mic is working?
Diethyl M-toluamide is the active ingredient in many insect repellent preparations. Following is one of the steps in its synthesis.
Okay, very good. So what they want us to do here to give the product. I also want to use this opportunity to write the mechanism for this. How many of you have used DIT before? DIT, this product called DIT, is an insect repellent. If you have used this before, give me a happy face. How many of you have used DIT before? Particularly in the summer when you see all those mosquitoes all over the, exactly. Okay, so this molecule we are going to synthesize now. Now, what they have here, very good. So what they have here, you have diethylamine. Diethylamine simply is this here. Amine, you have ethyl. Say diethylamine. Okay, I believe we are going to study the chemistry of amine in chapter 14. So anyway, so this is just giving us a little bit of a prelude to that chapter. Now this is diethylamine. And diethylamine, because you have on nitrogen here, you have a pair of non-bonding electrons. And so nitrogen has the ability to act as a base as well as a nucleophile. So what we are going to see here, we are going to see nucleophilic acyl substitution reaction. So remember when we discussed this chapter in class, for you to make an amide, you react an acid chloride with an amine, you get an amide. That is what this is. So in this particular instance, this will be the product. We are going to replace the chlorine. So this is the product here. That, replacing the chlorine, that, 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 and this is DIT. This is the insect repellent, the one that you use to spray on your body in order to repel those insects during the summer. Okay, this is DIT right here. Now, of course, the process that we've gone through here is what we know as nucleophilic acyl substitution reaction. So let us give you the mechanism of this reaction. This is just a way to refresh your memory. So we are starting with okay, this is going to attack this. So what is going to happen first? Does anybody have an idea what will be the first thing that will happen? The nitrogen is acting as a nucleophile. What will be the first thing that will happen? Non-bonding pair of nitrogen attacks carbon. N attacks, exactly, attacks. Very good, very good. So it attacks that. And in so doing, this pi electron goes to oxygen. Keep in mind, in this attack, I know many of you have asked this question before, how come we do not lose chlorine directly? That will not happen because this carbon here is an sp2 hybridized carbon. It is a lot more difficult to do a substitution reaction on an sp2 carbon. And that is why this chlorine will not leave directly. So, what do you get? You get this here. You get an intermediate. This here. Now we have this here. This here. The chlorine is here. Now we have the nitrogen here. Let me use a different color pen so we could see it better. Okay. So we have that. We have that. We see how the hydrogen attached to the nitrogen. So, okay, does anybody know what happens to the nitrogen now? Does anybody know what happens to the nitrogen? Do we have a charge on the positive charge? Exactly. The nitrogen now is positively charged. This is our intermediate. Now, it is now possible for this here, this intermediate to now want to regenerate the carbonyl. Keep in mind, this is a classic nucleophilic acid substitution reaction. Okay, I see Jessica is joining us. See here. So now we have this. We come back here, and when we do that, though, by the way, when we do that, the chlorine will leave, because if the nitrogen leaves, we simply go back to the starting material. But we have to move forward to go to the product. So we have okay, then we have this here. Now we have this nitrogen is here, with this hydrogen here, with this here, with this here. Okay, this is positively charged. And of course we know we have chlorine as left, which is somewhere here. So now what do you think will happen now? What will happen now? What will happen now? Anybody? Chlorine gas. Very good. Sinead said chlorine gas the hydrogen. I like that. Okay. So now chlorine will abstract the hydrogen. Chlorine will abstract the hydrogen. Will pick up the hydrogen. So comes here an acid-base reaction. And then, of course, in so doing, it will release the non-bonding pair of electrons back to nitrogen. And so we get this here. Keep in mind, we have the non-bonding pair of electrons right on nitrogen here. And that is the mechanism of that reaction. So now what we have formed now, we have now formed the insect repellent DIT, which means that insect repellent DIT is an amide. It is a tertiary amide. And of course, as you guys know, this is a very popular commercial product. But you can see how easy it is to make this. Okay? Now, if you follow this, give me a happy face. Okay, give me a happy face if you follow that. Okay, very good, very good. Okay, so now we've given you the a classic mechanism for the nucleophilic acid substitution reaction. Now, supposing, let me take this off. Supposing I want you to make the DIT from here. Supposing I want you to make the DIT from here. What will you do? Okay, I want you to make it from here. Can you give me the reagent that we need? Let me give you a hint. I want you to go through here. Okay, or you could go directly to here if you want. Either go through here or find a way to go to here. Indeed, give me two ways of doing it. Going from here to here. Anybody has an idea? Let us start with going through here first. Okay, chromic anhydride, very good. Reduce, no, oxidize. You need to oxidize the alcohol. At this point, you need to oxidize the alcohol. Okay, so you say step 1. Very good. Step 1, chromic anhydride, right? Okay, I could go along with that. In some acid. Then what do you do from there? What will be step 2? What will be step 2? What will be step 2? Because we want to make this. Thionic chloride. Excellent. See, all I'm doing is trying to give you guys a chance to practice your knowledge of reagents. So, what we did, we use chromic trioxide to oxidize this to a carboxylic acid. Once you get the carboxylic acid will react with thionic chloride to get the acid chloride. Very good. Now, supposing, since you've told us that we could do that, we could do this. Let us see this here. Since you told us we could do this, you said we could do this. Okay. Okay, so supposing I want to go from here to here, what do I do? What do I do? So giving you another chance to practice your knowledge of your reagent, what do I do? Go from here to here. What reagent do we need? This is a very bulky reagent, and we use an acronym. We use an acronym to describe, to give the name of the reagent. What will you do? You will still need to use this. You will still need to use exactly DCC. In other words, you take DCC. You could take the amine. You take the amine, diethylamine. Anytime you take an amine, and you have DCC, you could transform the carboxylic acid directly to an amide in the presence of DCC and the appropriate amine. In this case, this is the amine that we have. We have DCC, we get the product. Okay, if you follow that, give me a happy face. Give me a happy face if you follow that. Okay, very good. Okay, now let us see this. Yeah. Okay, let us do this one here. This will be the question of the day before we leave. Okay, a lot of people here that I have not talked to today. Okay, Jessica, is your mic working? If your mic is working,
from the table of available reagents, select the ones you would use to convert butanoic acid to each of the following products.
Okay, very good. Okay, now what do they want us to do? To convert butanoic acid. So, we need to know the structure of butanoic acid. I don't look at this here. Let's get this out of here. I could see Sinead now, smiling to herself. Okay, we take that. We take butanoic acid. The first thing they want us to do, they want us to make 1-bromobutane. 1-bromobutane, okay? So we go from here. 1-bromobutane, that should be fairly simple. Okay. How many carbons do we have in butanoic acid? How many carbons do we have? Okay, 4. How many carbons do we have in the product? 4. So we don't need to make a new carbon-carbon bond. All we are doing is going from one functional group to another functional group. In other words, we want to transform the carboxyl group to this carbon bromine bond. Okay. So what do we do? It should be fairly simple. Let us just do step 1, 2. Okay, good. Good. Lithium aluminum hydride. Great. So we could do step 1. So we don't need to write that out. We just say step 1. By the way, you guys could just simply refer to lithium aluminum hydride as LAH. If you want to save some time, call it LAH. That is for lithium aluminum hydride. And then we then say, after that we do what? After the LAH, what do you do? Before the bromine, we do the hydronium. And then step 3, somebody has given that to us, PbR3. Very good. PbR3. If that is clear to all of you, give me a happy face. That is a fairly simple one. Okay, I see most of you got it right. Okay, very good. Okay, let us come here. Do we have it right? Okay, are we right? G. Lithium aluminum hydride. So that is right here. Of course, they just do not follow these people's example. I do want you to show the hydronium or ion all the time. They are assuming that you add hydronium ion after that. Okay, so we have that. Then PbR3. Okay, so we are in business right here. Okay, very good. So now let me do my trick again. Okay, now we want to do this one here. We want to do this here. N-methyl pentane amide. Okay, so this gives us an opportunity to practice our nomenclature. Remember, we started with nomenclature? Okay, so the first thing we need to do here is to draw the structure of N-methyl pentane amide. Does anybody know what this is? What would be, how many carbon in the base name? Okay, let me give you leading 5 carbon. Good. So we have 5 carbon. So that means the base name is pentane amide, right? So if that is the case, we have pentane amide. If I say pentane amide, 5 carbon, pentane amide, so we have that is pentane amide. Okay, now what do we need to do next? It says N-methyl. What does that tell us? What does that? Okay, methyl is attached to nitrogen. Very good. So now we take off one of these hydrogen. Simply means we have methyl is here. So therefore we have a secondary amide. We have a secondary amide. So they want you to make this molecule from here. Let's take this out. Okay, they want you to make this molecule from here. So what do we do? If you look at how many carbons do we have? If you look at the longest carbon in the base name, how many carbon do you have there? How many carbon? 5. Okay, good. And then you have in the starting material, you only have 4. So that tells you something. That tells you you have to form a new carbon-carbon bond. Okay. And now we have to make a secondary amide. We already know how to make a secondary amide, right? Keep in mind, to make a secondary amide, you could either start with an acid chloride, react the acid chloride with the appropriate amine. In this case, if we take an acid chloride, the appropriate amine in this case will be this here, this part of the molecule. If we do that, if we react this amine with this acid chloride, we will get a secondary amide. Okay, we could either do that or we could do this. You guys already told us that we could do this with carboxylic acid, going straight to here, using DCC with this appropriate amide. Okay, so we could do that. So now our focus now should be on how to make either this acid or this acid chloride. That should be your focus. Okay, so let us go about doing that. I'm going to now erase this. Okay, starting from the carboxylic acid. So what do we do? Anybody has an idea? Okay, maybe I should give you some leading question. Okay, we want to go from this carboxylic acid now. We want to extend the carbon chain. Okay, how do you extend the carbon chain? How would you extend the carbon chain? Remember what you did in this problem here. What was the thing that you did here? You have to think in this particular problem. What did you do here? What was the first thing you did to make this? What did you do to make that? Okay, lithium aluminum hydride, exactly. Okay, so you did. Okay, so you did step 1, LAH. Step 2, hydronium ion. Then you say step 3, phosphorus tribromide, and you got this. You got this bromide. Okay, now, can you extend the carbon chain here now? Using this? Can you extend the carbon chain? Okay, let me say reduce. Yeah, that is correct. Yes. Okay, sodium cyanide. Exactly. You could do that. Or Grignard. Yes, you could do Grignard. Any one of those will do. Okay, so let us try Grignard first. Step 1, Grignard. Okay. And then, what do you do with Grignard? What do you do with Grignard? What do you want to extend the carbon chain? What are you have now formed your Grignard. What do you do with it? How do we extend the carbon chain? Okay, carbon dioxide, excellent. See what I'm doing here, giving you guys a chance to recall your reagents so you don't forget them. Carbon dioxide, then what do you do after that? Hydronium ion, right? Okay, very good. So at this point, what have we done? We have made our carboxylic acid. We have made the carboxylic acid. At this point, we have extended the carbon chain by 1, and that's all we need. Okay, now from here, how do we get to here? Anybody has an idea? How do we get to here, from here? We now want to go from here to here. What do we do? Okay, to go from, okay, DCC with amine. Excellent. So now you could take your DCC and then you use your appropriate amine. The way you know the amine that you need is you look at the nitrogen and whatever is attached to nitrogen, and of course you know that you're going to add one hydrogen here, so that becomes this one here. And you get your product. Okay? What other way can you do that? You could also, yes, we could try the, no, the LAH, you do not, LAH with cyanide will give you an amine, not carboxylic acid. Okay, so if you have this, we could also do this, right? We could also do this. Thionic chloride followed by the amine. You could do that also. That will also give you that. Okay? Now, supposing, like some of you suggested, that we want to go through the, want to form the nitride. Okay? We could do that also. Supposing we do that, change my pen. Supposing we take this here, we react with sodium nitride, which is essentially reacting with the nitride. The nitride will be acting as your nucleophile, and this will be an SN2 reaction. You will be displacing this bromine here because this is a primary carbon. So therefore you form this product here. You form that. Now, once you form that, what do you do now? Now, what do we do? Once you form that, what do we do? Exactly. Now you hydrolyze to form this acid. Okay? Keep in mind that if you hydrolyze a nitride in the presence of dilute acid, you get your carboxylic acid. So you see, there are many ways in which we can get to this. We could go to, of course, starting with this here, carboxylic acid. We form the alkyl bromide, and from the alkyl bromide, we could decide to go the route of the magnesium, add the carbon dioxide to it. That is the point at which you extend your carbon chain. Somebody wants to ask me a question, go ahead. And then, of course, adenine ion, then you get your carboxylic acid. Or you could take the alkyl bromide, react with cyanide in an SN2 reaction, you form the nitride, and then at that point you have formed your new carbon-carbon bond, and then from the nitride you come to the same carboxylic acid. And from this carboxylic acid, of course, you could decide to do DCC with the appropriate amine, or you could decide to go to the acid chloride, and then followed by the amine to get the product. Okay, so let us see what they have here. Do we have all the pieces? Okay, we have lithium aluminum hydride. We have the, okay, so, and then they did the PBr, so that is all here. Lithium aluminum hydride, we did that. PBr, we have that. And then we also have cyanide, which is what we did here. Okay. And then we then do the hydrolysis. Do we have, they give us anything for, okay, that would be this here. This hydrolysis here. This here, that would be this one here. Okay, that would be the version of hydronium ion. So that is that. And then, of course, now, okay, this is what they did here. After they did that, they now did the thionic chloride. They went to this route. That is what you have here. Okay, and then after that, then they did this. So we got all of the ingredients here. Okay, the only thing they did not do here, they did not go to this route. But this route is just as good. The magnesium followed by carbon dioxide, and then you form your carboxylic acid, react with DCC and the appropriate amine, you get your amide. Okay, if you follow that, give me a happy face. Okay, I think we are about to get 1 more minute before we leave. Before we leave, I do want to make a correction to the session we had yesterday in class. There was, when we discussed acid-base reaction, I think there was a point I was making. I don't think I made it very clear, because I went back to look at the video, the webcast for the session. I said, oh my God, the student will be a little confused here. So let me clarify this. Remember, I gave you this here. And I said we react with hydroxide. And I believe I gave you an arrow. The arrow was pointing here. That was wrong. The arrow should be pointing in the other direction. The arrow should be pointing here. Okay, and I said we got the enolate anion. Okay, and then we got water. Okay, and I told you, of course, the pKa value. If you look at the pKa value, so this pKa was 20 for this hydrogen here, 20, and the pKa for water is about 16. And I told you that reaction goes from strong acid. Generally, most reaction goes from strong acid, strong base to weak acid, weak base. That is the direction those reactions generally go. In this case, this is the strong acid. Keep in mind the pKa of water is 16. The lower the pKa, the stronger the acid. So this is the strong acid. And this is the weak acid, which means that this is the weak base, this is the strong base. Which means that this is the weak base, the hydroxide. I think what I gave you an arrow that went this way. Actually, the equilibrium is favors to the left. A little bit of the reaction will go to the right. Okay, I also told you that we could still use this reaction to generate enolate anion, even though it is small, but the reaction will still continue, because what happens, once you form your enolate anion, you begin to alkylate this enolate anion. That will drive the equilibrium to the right. If you follow, if you remember Le Chatelier's principle that you did in general chemistry, that is what is happening here. Any system in equilibrium, if you do anything to upset the equilibrium, the system will go in the direction where you are upsetting the equilibrium. In this case, if you try to remove this out of solution by alkylating this, the equilibrium will be driven to this side. But just based on acid-base reaction alone, the equilibrium is to the left. So I just thought I should clarify that that particular concept, so that when you look at the webcast, you don't get any confusion. Okay, is there any question before we leave today? Is there any question? Okay, I see no question. Okay, I see a couple of people want to talk. Let's see here. I see a lot of people are still with us. Bea, Funke, Brittany. I didn't know that Brittany joined us. Dia is here. Emmanuel, I didn't see these people earlier. Okay, everybody, I hope you all enjoy the rest of your evening, and I will see you in class tomorrow. Unless you have a question, I will stay around for about 1 more minute.